everybody, welcome back. This is Math 21 at College of the Sequoias. It's Introduction to Statistics. And we're going to wrap up our probability section on this is on counting techniques. This is 5.5 in our book. If you're using a different book or at a different college, it might be a different section, but this is on counting techniques. And let's do a segue. Let's start off with an example and lead into it. So the typical California license plate, or at least it used to be, I don't know if it's changed. It used to be, it's 7 characters. And it usually goes a number, a letter, a letter, a letter, and then 3 numbers. So pound key, that represents number, and L represents letter. And I have 2 questions for you. How many different combinations are possible? And what if we don't allow repetition of characters? Or don't allow characters to repeat? Now, each of these is independent of the character before it and the character after it in the first one. So you can use your multiplication rule for independent events here. Probability that the first one is a number times this probability that the second one, well, that's probability of one given thing. How many different numbers are possible? We've got 0 through 9, which is 10 numbers. And A through Z is 26 letters. So the different combinations is 10 numbers possible in the first lot, 26 letters, then 26 letters, then 26 letters, then 10, then 10, then 10. This was just like doing the 2 dice. You multiply the number in each category times how many are in that category. And if you multiply this out, this is 175,760,000. So the probability of having an exact match or specific plate, there's only one plate that has it because they don't repeat license plates. That would suck. That would make it so cops couldn't do their job. Only one car has that license plate out of 175,760,000. That's a really small number. Now, if we disallow repetition, what happens? Well, the first number is fine. It's still 10. And the first letter is fine. It's still 26. When I get to the next letter, though, let's say I used A already. I can't use A anymore, so I could only use B through Z. That leaves 25 letters. And let's say I used B for the second one. Let's say this was 9AB 76. I need another letter, C 765. So I get to C. At this point, A and B have been chosen. 2 of the letters are gone. We can't choose them. There's only 24 letters left. And when I get to the second number possible, well, I've already used up one of the 10. I can't repeat the 9. So there's only 9 numbers left. And so let's say I chose a 7, and now I've chosen 9 and 7. There's only 8 numbers left for the third number. And now I've chosen 9, 7, and 6. There's only 7 numbers left for the fourth number. So that's my example plate. 9AB765. That's no repetition. And if we multiply that together, this is 78,624,000. This is the multiplication rule of counting. Okay? If the first option has P choices, second option has Q choices, and if we did a third one, let's say the third option is R choices. I'm using letters because I'm not specifying the thing. Like this could be a meal, dinner meal. And this could be our appetizer options, our entree, and maybe our dessert. The number of combinations available or in the example I gave, in my example, number of possible dinner meals. You just multiply the values, P times Q times R. And if there's more choices, just keep multiplying if there's more choices. Now, to continue, I need to discuss something that you may not have seen for a while, but it's important. So there's something in math called factorials. Factorials, I even have it on my calculator. It's right there. It's the yellow letter right there. It said value followed by an exclamation point. That's a key on my calculator. I have to hit shift on my calculator to get to it. What this equals is x multiplied by x minus 1, multiplied by x minus 2, and you keep going down depending on how big x is, multiplied by 3, multiplied by 2, multiplied by 1. For example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. On some calculators, you might see a PRB key. My calculator doesn't have it. Is on some calculators, and it's used in this section as well. And where we're going to use it, we're leading to the PRB on a calculator usually has these options. It usually gives you n factorial n, lowercase n, big C, lowercase r, and lowercase n, big P, lowercase r. And we're going to discuss each of those here. Here, n factorial is the same thing as x factorial. There's some important things to note with factorials. More rules of factorials. It may seem obvious, but 1 factorial is just 1. And we define 0 factorial to equal 1. And it's defined that way. And this breaks the general strategy of reducing by a number each multiplier. Okay, those are the rules of factorials. You just have to accept that, and the reason why, this is a hard rule. It has to work, and the reason why we define it that way is it's defined this way to make the following equations work. Before I list the following equations, I need to go over 2 ideas: permutations and combinations. This goes by Npr and Ncr. These are on my calculator. I'll show you on mine if you have one similar to me. Ncr is right there on the calculator. It's the button. And I don't know if you can see it very well. If I want the Npr, I have to hit the shift key and then hit the Ncr, and it'll give me Npr. And I'll show you guys in a second me using it. I don't have a calculator with the PRB. I can't show you that here. You'll just have to tinker with it a little bit. So what is N and R here? N represents the number of distinct objects. There's N distinct objects. And R is the number of objects selected out of the N. Okay, I'm going to start with permutations. Permutations, which is something that is kind of going downhill in society in a lot of, like the way they teach children. Permutations, order of selection matters. And what I mean by this, they're not teaching the children. They teach everyone's a winner and get sports when they're kids now. Everyone gets a trophy. And in reality, there's a first place, the team that did the best, second place, third place. And if you're in first place, you can't be in second or third place. You've already won your spot. So that's one example. Clubs often pick people. Another example, they picked like the president, vice president, secretary, treasurer. Some clubs have more positions. That's permutations. Combinations. Order doesn't matter. A perfect example of this is the lotto. Whether you played it or not, you have to have known about it by now. You pick a certain amount of numbers. Generally, it's 6 numbers out of maybe 52, 80. Keno is 80 numbers. California Lotto, I forget what it is. We could look it up later. You pick 6 numbers. It doesn't matter what order you write them down in. It doesn't matter. They have a ball blowing machine. It forces 1 ball out at a time. They do the first 6 balls. Doesn't matter what order the balls come out in. As long as all 6 balls match the numbers you got, regardless of the order they pop up, you win. Okay? You win the big prize. So order doesn't matter. The lotto is a perfect example. Let's look at the formulas for permutations. We got NPR. Again, N is the number total, and R is the amount selected. And order matters. So horse racing, let's talk about the trifecta. Trifecta in horse racing. It might be in other forms of racing too, like dog racing, maybe car racing. I don't know if they call it the trifecta there. When you bet on the trifecta, you pick first, second, and third place. The simplest bet in horse racing is just betting on what horse is going to win the race. That's betting on who's in first place. You can bet on who's in first and second, or you can bet on the top 3 positions. What horse is first over the line, what horse is in second, what horse is in third. And it's all one bet. If you get the right 3 horses, but they're in the wrong order, you lose. Okay? That's why order matters. So let's say for our example, they generally don't do a lot of horses. Let's say there is 12 horses. That might even be a little high. Let's say there's 12 horses and we are selecting 3 for the trifecta, first, second, and third. That means my N is 12 and my R is 3. Oop. N is 12, R is 3. Okay? And this is just going to show the number of possible permutations, shows the number of possible outcomes. And the formula for NPR is n factorial over n minus r in parentheses factorial. So in our problem, we have 12p3. Let's just show it on the calculator real quick, and then we're going to do it by hand. I think this area is a lot better by hand. It's a lot easier by hand in a lot of circumstances when you're trying to simplify, as you'll see in a little bit. So I'm going to do 12 Then I'm going to hit the shift key. And NPR is above NCR. So when I hit shift and then NCR, a P pops up. That's telling me I'm doing permutations. And I'll hit 3 for my R. 12P3 is 1,320. Okay. Formula-wise, this is 12 factorial over 12 minus 3 factorial, which is 12 factorial over 9 factorial. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Bottom is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You'll notice that all of these cancel with those right there. This ends up being 12 times 11 times 10, which is 132 times 10, which is 1320. An easier way of looking at that without writing them all out, I'm going to do the same thing, makes it a little clearer if you're doing it by hand. If you're doing the factorials like this and you're canceling them out, go across the top, write them out until you get to the number on the bottom, and leave that as 9 factorial like that. I could write out 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. I could, but I've already got 9 factorial on the bottom, and they just cancel out right there. 12 times 11 times 10, 1320. That is the number of possible ways we can pick 3 horses out of 12 for first, second, and third place. Okay? So, assuming that all outcomes are likely, assuming that any outcome is as likely as the others, for a uniform sample space, it's uniform when they all match. The probability of winning the trifecta, there's only one winning ticket out of 1,320. 0.00758. This is a highly unusual event. Which leads me to a fun story. When I was maybe 12, 11, my brother's 1 year younger than me, my cousin took us to the horse races. And my mom gave us money. It was at the state fair in Sacramento, in California. I used to live in Sacramento. We went to the fair and she wanted to go to the races. And she let us bet on one ticket, and it was the trifecta. Our cousin did. Me and my brother each had 20 bucks to spend at the fair. This was a long time ago, so 20 bucks went a long way. And a trifecta ticket cost $2, and you bet on 3 horses. And she was trying to show us that gambling is bad, that you lose your money. Now, I didn't know a damn thing about horses. I didn't look at them. I went and looked at their names. They all have cool names like Lucky Gallop or Thunder Hooves, or, some crazy names. I hit the trifecta. I bet $2. She bought the ticket for us, and I hit the trifecta. And did she give me my money for the fare? I don't remember how much it was. It was like 80 bucks or 90 bucks, 100 bucks. It was a good chunk of money. Way more than the $2 that I bet on it. No, she didn't. She took it home and she gave the money to my mom. It did not make it wasn't good for the lesson, so I didn't get my money. I got screwed. That was my cousin Annette, long time ago. So that's permutations. Order doesn't matter, or order does matter. If we look at combinations, order doesn't matter. The N and the R still mean the same thing. We use NCR. This is a calculator button. This is very similar to the permutations. We've got N factorial on top. We've got N minus R parentheses factorial on bottom, but we also have another R factorial on bottom. And this is read, the way we read this, as N choose R. Let's say, let me give an example. I'll put that right there where we can still see it. My example is I have let's say I have 21 students in class. And I decide to randomly give three people an instant A. They don't have to do any more work in the class. I'm just being generous. I would never do this. Don't ever think I would ever do this. No teacher would ever do this. But it's a way of describing it. You're in the class. Do you care if you're the first student selected? Second? Third? No. As long as you're selected, you're happy. Now, this isn't true for all students. Some students would be upset if I gave them an instant A. They want to earn what they get. And that's the right attitude to have. So, I'll write down my formula again. N choose R is N factorial. We've got R factorial and then parentheses N minus R factorial. In this problem, I have N is 21 students and I'm going to choose 3. 21 choose 3. Or 21 C3. 21 factorial over 3 factorial and 21 minus 3 factorial. It's easy to work out by hand. That ends up being 21 factorial, 3 factorial, and then 21 minus 3 is 18 factorial. So along the top, I'm going to go down until I get to 18. 21 times 20 times 19 times 18 factorial. Then I'm going to write out my 3 factorial, 3 times 2 times 1 times 18 factorial. The factorials for 18 cancel, and I can try to simplify. 21 divided by 3, 21 is 3 times 7. I can cancel out the 21 and the 3, and it leaves behind a 7 on top, a 1 on bottom. 20 and 2 have a common factor. This is 2 times 10. So I can cross off the 20, leave a 10, and cross off the 2, leaving a 1. So what I have is 7 times 10 times 19 on top, 1 times 1 times 1 on bottom. Well, those are 1s also. Having a 1 on bottom doesn't matter. This ends up being 1,330. So there are 1,330 ways to select 3 people out of 21 when order doesn't matter. Okay? Now, let's take a look at that problem we talked about a while ago. There are 30 students, 18 girls, 12 boys. And I randomly select 4 people. What is the probability that at least one is a girl? All right, so I'm going to do a couple approaches. First approach, let's reason it out. Well, is that really what I want to do? Reason it out? Let's see. At least one is a girl means 1, 2, 3, or 4 girls. The only other option is 0 girls. So the probability of at least one and the probability of 0 girls have to add up to 1. These are complements. We are looking at 1 minus the probability of 0 girls, which is 1 minus the probability of all boys. Which is 1 minus the probability that the first is a boy, and second is a boy, and third is a boy, and fourth is a boy. And this is similar to the one where we did probability of F and E equals the probability of F given E times E, where I did the pocket aces one. Well, the probability that the first one is a boy, how many students is there? There's 30 students. There are 12 boys out of 30. And then the second one being a boy, well, there's only 11 boys left. And now there's 29 students left. And this one is now on the third one. We've already selected 2 boys. There's only 10 boys left, and there's 28 students left. And for the fourth one, there's only 9 boys left out of 27. Some of this stuff simplifies. Okay. Let's take a look at it. Well, the 10 and the 3, I can, 10 and 30. 10 goes into 30 3 times. I can cancel that out. 9 goes into 27 3 times. I can do that. Cancel out the 9, leave a 3 on bottom. 11's a prime number. It's not going to do anything. 12 is 3 times 4. And 28 is 7 times 4. 12 is 3 times 4. I can cross off 4s there. And I'm left, let me just clean it up, see if anything else cleans out. I got 1 minus 3 times 11 on top. On bottom, I've got 3 times 29 times 7 times 3. All of those are prime numbers. That doesn't get any cleaner. So that is 1 minus 33 on top. 3 times 29 times 7 times 3 is 1827 on bottom. If I get a common denominator, 1827 over 1827 minus 33 over 1827. $1,794 over 1,827. That's the probability of at least one girl. What is that? If we divide that, I'm getting approximately 0.982. Okay, we're going to use the same numbers, and I'm going to do it with the NPR and or Ncr. I'll show that to you. So option 2. Still the same thing. We're going to do 1 minus probability of 0 equals probability of at least 1. Well, how many ways can I select? No, that is the way. That's the best way. 0.982 right there is doing that. What I wanted to do with this other one isn't as helpful. Let's just leave it at that. There is one other thing that pops up in this category. And this is when we have, the other thing in this category is non-distinct objects. Let me check something. Is that correctly? Something looks like it might be off somewhere. The other thing in this category is when we have non-distinct objects. And this is what's going on. How many ways can I arrange 10 flags let's just say in a row? If I have 5 white, 3 blue, and 2 red flags. Now, all the blue flags look the same and all the white flags look the same. These are non-distinct. So let's say, oh, let me do 10 spots. And we can kind of reason out what's going on, and I'll show you what we get. Let's say I do the white ones first, and let's say I throw a white one here, and maybe down here, and here, and here. I am choosing, I have 10 flags, and I am choosing 5 positions. 10 flags are left. Choose 5 positions for the white. That's going to give me 10, choose 5. And now I'll do the 3 blue flags. Maybe I should have used red ink for the red flags and blue ink for the blue flags. Well, we'll do that for the blue. Now I've got 5 flags left to place. And I'm going to place 3. So I'll put a blue, we'll put blue here, blue here, blue here. I had 5 places to choose from, and I chose 3 of them. 5, choose 3. And finally, I get down to my red flags, which will be in green. Well, I've got 2 flags left. They're both red. And I've got 2 places to put them. So red and red. 2, choose 2. What this ends up being is I can multiply these. 10, choose 5, times 5, choose 3, times 2, choose 2. I'm going to write out what they are in the factorial form. What's going on here? Whoa. I think that zoomed a little bit. There we go. Yeah, I did. That little yellow square was irritating me. All right. So remember NCR, n factorial over r factorial, n minus r factorial. Which gives me, for 10, choose 5. I've got 10 factorial, 5 factorial, 5 factorial. And then I do 5, choose 3. This is 5 factorial, 3 factorial, and then 5 minus 3 is 2 factorial. That's my 10 minus 5. That's my 5 minus 3. And then I do 2, choose 2. 2 factorial over 2 factorial. And 2 minus 2 is 0, 0 factorial. I told you we needed 0 factorial to equal 1. Now let's look at what cancels out here. I've got a 5 factorial here and a 5 factorial there. I can cancel those out, leaving behind a 1. And I got a 2 factorial here and a 2 factorial here. I can cancel those out. And what I'm left, and the 0 factorial equals 1. So what I'm left with is 10 factorial over 5 factorial times 3 factorial times 2 factorial. Now I can work that out, but I want to point out something. How does that relate to our starting information? To the given information. Well, there was 10 total flags. So I've got the total factorial on top. And then my first flag option was white. So option 1 factorial. And then the next one is 3. Well, I had 3 blue flags. Option 2 factorial. And then I had 2 red flags. Option 3 factorial. That matches up with the 2 factorial. So, in general, for non-distinct items, if we have n items divided into k different groups, so group 1, I'll call N1 is the number in group 1. And we go all the way down to group K, where Nk is the number in group K. So group 2 would be N2, group 3 would be N3, group 4 would be N4. What we get is n factorial over n1 factorial maybe I better use capital N's. Times n2 factorial times, keep going, multiplying until you get down to nk factorial. That is the number of possible combinations. That kind of wraps up chapter 5. Another example of Lotto. Let's do another example of NCR Lotto. Let's say there's 52 balls, 52 numbers, and we choose 6. The order doesn't matter, so we're going to have n equals 52, r equals 6. 52 choose 6. Probably easier in a calculator. 52 NCR 6 shows a C on the calculator. See that? 20,358,520 combinations. in total. That's the total number of ways 6 balls or 6 numbers can be chosen out of 52, where order doesn't matter. So the probability of getting 6 out of 6 correct, there's only one ticket that has that. 1 out of 20,358,520 is a really small number. 0.000000049. Way, way less than a 1%. All right, that wraps up 5.5. We've only got a couple more sections till the midterm. Peace.